Hello, and welcome to Physics for Play. In the last episode, we talked about how to solve a system of two coupled oscillators. Today, we're going to show how to use normal mode analysis, which you can use to solve more complicated systems of oscillators. Let's get started. So, how do we solve the more complicated system? And what exactly is a normal mode? And what does it mean for our coupled oscillators? And what the heck do I mean by an eigensystem? Well, to start, a normal mode of an oscillating system is a pattern in which all parts of the system move sinusoidally with the same frequency and with a fixed phase relation. So what that means, if I go back to our simulation, is that if I look at the motion of our oscillator here, they are moving, both of these masses are moving in phase, and they're moving with the same frequency. And then the same thing for if I were to go back and put them out of phase. So I'll start them out of phase. You can see now they move out of phase. They're out of phase, but they're moving with the same frequency. Even if they're out of phase by 180 degrees. So those two modes are the normal modes of this system. Now, it turns out that if you take a set of linearly coupled oscillators, they make up what is known mathematically as an eigensystem. And an eigensystem has the following characteristics. Generally, you have some matrix M, and for that matrix, for a given matrix, there exists some vector such that when you operate the matrix on that vector, take the dot of the two here in Mathematica speak, you just get a constant times the same vector. So I take the vector, operate it on it with the matrix, and you get a constant lambda times the original vector. Here, that constant lambda is called the eigenvalue, and the vector x is called the eigenvector. Now, we are going to write our vector x as being some combination of the initial positions of the two masses. So we're going to say x is equal to x1, comma x2. And we are going to do some kind of variable transformation, some linear transformation combining the x1s and the x2s in such a way that this relationship holds. And we can do that because we can write our equation of motion using a matrix format. So if I scroll up to my equations of motion, we have force as mass times acceleration, which is the second derivative of position with respect to time. And that equals minus, for x1 it equals minus k plus k12 times x1 plus k12 times x2. We can just write that as a matrix, as you can see here. In this case, the matrix is going to be equal to k plus k12 over m minus k12 over m, etc., etc. We're going to go ahead and evaluate that, and we'll write down the equation of motion, x double prime equals m x of t. Now, just a reminder, the m is the matrix here. It is not the mass. And, actually, I should quit my kernel because I want to do this in variables. So I'll run this one more time. I'll run that one more time. And I'll run this, and we'll see what our result looks like. Now, looking at our equations of motion, you see mass times acceleration equals minus kappa plus kappa 1, 2, x1 plus kappa 1, 2, x2. And we've got a list of equations here. but the upshot is you've got the acceleration. The mass is just over here on the other side. But the mass times the acceleration would be kappa plus kappa 1, 2, x12 minus kappa 1, 2, x2. So you've got the same equation of motion here, just written out in matrix form. So what we can do with this matrix is, now that we've written down the matrix, we can actually make this the following statement, which is that there exists some combination of displacements such that we can show that this is an eigensystem. Specifically, when I take m times an eigenvector x of t, that is going to equal minus omega squared times x of t, where minus omega squared is your eigenvalue. That eigenvalue is actually equal to the angular frequency of the system. Or I should say the omega in the eigenvalue is equal to the angular frequency of the system. I'll point out that all we're really doing here is a variable transformation. So we're going from a vector that has two components, where the first component is x1 and the second component is x2, to a version where we get a mode that where our two components of the x vector are x1 plus x2, and then the second component is x1 minus x2. Now, geometrically, this just corresponds to, it's almost like a rotating your eigenvector in space. What we can do, though, is let's actually show you how to do that in code, though. So we have our matrix M, and by the way, I am skipping a whole bunch of steps along the way here. I highly recommend, because there's some minus signs that I've been playing very fast and loose with. So I highly recommend going through the actual linear algebra for this, which you can find in pretty much any standard differential equation book. I think you can even find it on like a Wikipedia page if you search for Eigensystems. But since I don't want to do any of that, because as we've said many times on this in this video series, I'm incredibly lazy. We're going to just do it with Mathematica. So I am going to say that my angular frequency, actually I'm going to say my angular frequency squared is going to be the eigenvalues. That will get us, so we'll take the eigenvalues of the matrix M, and you can see, actually, I mentioned I was playing fast and loose with the minus signs, and you can see that here, because I should have, this should be minus x squared, so I should have a minus sign here, and I think what I'm doing is I'm missing a minus sign in the matrix, because, yeah, because the x1 term in my first equation should have a minus sign in front of it, just like it does over here. So sorry about that. We'll put that minus sign back in. That goes like this. Now my x equation looks more like it's supposed to. It's got that minus sign where it's supposed to be. If I evaluate this, I get the eigenvalues minus k over kappa over m. I've got this other minus sign, and we see that the matrix equation is minus omega squared. So this should really be, if I want to solve for omega, omega is really going to be minus this, and then square root of the whole thing. And I'll throw a simplify on top of that just to make it look a little nicer. So those are your eigenvalues. Now, if you want your eigenvectors, we can do the same thing, except instead of the mass m, the eigenvalue rather, operating on mass m, we'll use the eigenvector function, because Mathematica is your friend. Now, I should have pointed out, remember, we showed before that our modes were oscillating in phase, in which case the two displacements get added together, or they're out of phase, in which case there's a minus sign between the two. And you can see that's exactly what we have for the eigenvectors. They're either in phase, so x1 gets multiplied by 1, x2 gets multiplied by 2, or one of them gets multiplied by a minus sign and they're out of phase. So you can do this. The last point I'll make on normal modes and eigensystems is you can do this for any number of oscillators. It's just that your matrix gets bigger. So if I had 3 oscillators, instead of having a 2 by 2 matrix, you would have a 3 by 3 matrix. If I had 4 oscillators, instead of having a 3 by 3 matrix, you'd have a 4 by 4 matrix, and you'd have 4 normal modes that you'd have to find. So the number of the dimensionality of your matrix, or the number of oscillators, I should say, that just tells you how many normal modes you're going to have. So the last thing I'll point out is there's a lot of really interesting physics that you can play with that we're not going to get a chance to touch on. But I would recommend going through and trying your hand at some of these. What other things can you find with the physics that we've created? Can you make a new oscillator system? What would the force system look like? Here are some questions to get you started. What happens when you add a damping force to coupled oscillators? How does that change the system? What happens when the oscillators have different masses? So we started with a system that had 2 masses, but they were identical masses. What happens if one's 1 kilogram, but the other one is 3 kilograms? I guess I already answered this one. How many normal modes will you have for 3 oscillators? In one dimension, at least, there will be 3 normal modes. And what will those normal modes look like? What would it look like if you had n oscillators? What happens if you include a driving force? Are you going to get resonance? And if so, what frequencies will you see those resonances at? Since we've already shown that you're going to get different, you'll get multiple frequencies that are related to your eigenvalues. And then what happens if you include nonlinear forces? So what happens if we include something like a Lennard-Jones force? So let's say we're describing some molecules that are bonded together. You have a Lennard-Jones force describing the interactions of those molecules that are bonded together. What is the mode? What do the normal modes look for a system like that, where you have nonlinear and harmonic forces? Well, that is all for this time. Like the video if you liked it, and if you'd like to see more of these, please click subscribe.